Hi, I'm Jody Hagins, and I'm here today to talk about template metaprogramming with some practical application. One of the great things about being on a Friday is that you've been able to participate all throughout the whole entire week, not really having to worry about too much until the end. One of the bad things about it is that you end up talking with people about your talk throughout the week, and you may do the stupid thing that I maybe have done, and that's take the things that people just seem to be most interested in and reframe your talk to go around those things. But we're going to talk about things that you run into when you're actually doing metaprogramming. Try and give some practical advice or input and insights into some of this stuff. So this is basically just a type identity. We'll see this throughout. If you have C++20, you've got that. And what we're going to talk about first is this thing called void t. Void t is one of the simplest, yet most powerful snippets of code that you may ever encounter. It's got tons of utilization. It's very powerful and very simple. For those of you not familiar, because this is more of a tutorial style, and I will say that if you have, I'm more interested that you understand what we're going through. So if you have questions about something, ask. If it's something you think I may get to later, wait, because I'll have several different places to ask questions, but just ask a question if you need to. So, that template and using thing means this is an alias template. Those dots mean 0 or more things, and the type name here means that the alias template has 0 or more type parameters. And it will always give you a void result. So this idiom is explained in much more detail in Dr. Brown's 2014 two-part talk, which by itself was one of the best videos of any kind that you'll ever watch. So if you haven't seen it, I encourage you to do so. If you have seen it, it's kind of like The Princess Bride. You can't see it too many times. And so we're going to run through the following slides that are going to give some information about this, but I'm going to go through the next ones kind of quickly because most people have probably seen something about this. And I want to get into some cases that happen when you try to use void t and it doesn't work. Or it doesn't work how you don't get what you think you might want to get. So first, void t always evaluates to void no matter what you give it, provided what you give it is a valid construct. And in this case, we are giving it an int, ref, a reference to an integer, and we're going to get back void. But what if we give it a reference to void? As we know, a reference to void is invalid. So we're going to get a hard error in that static assert because we got a failure. Reference to void is illegal. And so we get a hard failure. So remember this because we're going to see it again really soon. So let's try to implement a meta function, add L value reference. Okay, here's some static asserts. Here's what our add L value reference should do. If we feed it an int, we should get an int ref. But if we feed it a void, we should get a void. Also, if you feed it one of those things that it says, if it's a CV or modified function, basically that means like the member function, you're going to get void too. Things you can't take a reference to, you'll get echoed back that type. And that's what the standard says. Anything else, if you can take a reference to it, you'll get its reference. Okay. So this primary template has two parameters. The second one, which defaults to void. And note that it will return whatever type we give it because it inherits from type identity. And remember, type identity just says that its type is the type you give it. And if we look down here at these asserts, we'll see that if we don't provide any more code, that the second static assert will pass, but the first one will have issues. Because all we're doing is echoing the type. So that first static assert is just going to return int. So that right there, that will fail. So if we provide this specialization, this right here means when tref is valid. So if you can actually, remember I said void t will return a void if what you give it is valid? If you give it something that's valid, then it's going to resolve to void. If not, then you're going to get an error. Remember that hard error? Well, we don't see the hard error. We'll talk about that in a second. But what this means is that the call to void will resolve to void, and since it matches the default, right? It matches the default, then this will be chosen because it's a better match. And so we will have, all of these asserts will now pass. All right. So when t is an int, then tref is valid, and the result will be intref because both the primary template and the specialization are valid. But the specialization is more specialized, right? Because it is the specialization. And it's chosen. But note that its void has to match the default parameter that we gave the original primary template. And so when t is void, then remember forming a reference to void gave a hard error before. Well, it's still a failure. It still creates an error. But the failure is not treated as an error because it's being substituted in a dependent context. And so this failure is treated as not an error. It's, this is not the droid you're looking for. This is not the error you're looking for. Go away. And so the compiler silently ignores the failure. And we fall back to the primary template. And so the result will be void, which is the same type that was given as input. And so this can easily be read as any type you give me, I'm going to return that type that you gave me, unless you give me a type that I can bind a reference to. And in that case, I'm going to add a reference to it and return it. And the void t here allows us to specialize based on a construct that may or may not be valid. So if the construct is valid, then it will resolve to void. If it's not valid, if it's taken in a non-deducing context, then you'll get a hard compiler error. But if it's taken in a Sphene-friendly context or in a deducing context, then it will just silently go on and look for the next best thing. So how is void t implemented? I call this a pure or direct alias template, for lack of better terminology. If somebody has a better term, go ahead and give it to me. And I am not a core language expert. I want to go on the record for that, in case you might be confused. And the following is only the result of my investigations into these issues that I had. So how I first came across issues with using void t is I had my own void t, and then when C++ 17 came around, I converted all my code to use std void t, and I found places where I was getting compiler errors. And I'm like, this should not be. What have I done wrong? And so I go and look in there, and what we see is that there actually are some open issues. There's one that I think is directly relevant to this case that I'm going to be talking about here. And there's some others that are similar, that are linked to it. I bring these up because I'm going to address some issues in which, in practice, when you use void t, you may come across some places where you might think that it's broken, but it's not broken. It's just a victim of these issues that are in the core language, which, as far as I know, because I've been trying to track it and look at it, they still have not been resolved. And they've been around since like 2014. So the first example is something that I actually ran across on Stack Overflow as well. I think this was Vittori. I think this was his. Anyway, here's the actual code. So the function overload will be enabled if t has a type alias x, right? Does that make sense? So this first function overload basically says that if the t you give me when you call func, if that t has a type alias named x, then it's going to match, and this function will get called. The next one says that if the type that you give me has a type alias named y, then this one will match. And if they don't match, then remember, this will be a substitution failure, which is not an error, right? So it just won't match. But if they do match, then that's what will happen. So in this case, when we call func1, notice that 1 up there has an x. And when we call func2, note that 2 has a using y equals int. Okay? So we run this through our compiler, and we get something that looks like this. And we go, why is this happening? It seems like maybe a reasonable usage of void t. We haven't done anything wrong. We've just said, I just want to give you something, and if it's going to match. And I'll call your attention to, first, so that basically it says that there's a redefinition of func, but we know it's not a redefinition. Now, we might think it would be a redefinition if you look at, but what we have is we have the type, it's a non-type template parameter equals null putter. If you had that as type name something equals a type, then yes, you can't do that because that's not part of the signature. You can't do that, right? But this is not the case. These are non-type template parameters. So to explain what's happening, let's make some small changes. All I really did here is I replaced stood void t with blarg because blarg is one of my favorite words. It means nothing, but for some reason, ever since I've been programming, I've used blarg for something. So all we did was replace it. We get the same compiler errors as we would expect because all we did was replace stood void t with blarg. Again, no major change. We just got rid of the void, right? That sounds like maybe a movie or a Star Trek episode. Anyway, we just got rid of the void by replacing it with a struct. Because void does have some special rules, so maybe that has something to do with it. But we get the same compiler errors as we would expect. Again, not a major change. All we did was we replaced using blarg equals blarg t with struct blarg colon blarg t, curly braces, right? So instead of blarg being an alias, it's now just a class template. But there is one more important difference about this code. Anybody recognize what is the important differential between this code and the code on the previous slide? It is declaring a new type, yes. The real important difference is subtle in that this actually compiles, right? This compiles. And it actually, it doesn't just compile, it compiles the way that you would want it to compile and the way that you think it should compile. So we can implement void t like this. We can basically have, I always have this struct called first, and where I grab the first piece, right? You give a type and 0 or more types, and you just want to return the first one. And then void t now is not a direct alias, it's an indirect alias. And again, I think I made up those words or read them somewhere. I'm sure they're not official. But it's not just saying void t equals void. It's going through another mechanism, so it's indirect. And if we do that, this is the exact same as the first example, except where stood void t was, now we've got our void t. That's the only difference between this and the original example. But there is one other major difference, and that's that now the code compiles and it works exactly as you would expect it to work. So there's not much difference between stood void t and our void t, but there's clearly a difference in behavior. So if you're using void t as a way to grab your specializations or as an enabler, and you run across things where it says it's duplicate, it might be due to this issue. So here's, if we look and see, void T is a pure or direct alias template. Our void is an indirect alias template. Looking at another example, now this example I did, you can tell because it has foo blarg in there. It's almost identical to the example in Dr. Brown's original presentation. Okay, so this was the intent. The first is when foo blarg with T and U have a static value. Okay? So this one will be enabled if foo blarg of T and U, if that class has a static value. The second one, if T has a member ZZ and U has a member YY. Okay? Either of these in isolation with std void T will compile, but when you put both of them together, you get this wonderful error. And it happens to be reminiscent of the one we got previously. And it's because of a similar but not identical cause. But if we go in here and use our void T instead of std void T, then we get the behavior that we're looking for, and everything compiles as expected. Another example, and this one is mostly to Clang. Now, partly it's because those core issues, in 2014, there were already divergent implementations based on the issues that were in those core issues. So it doesn't surprise me that this code returns false on GCC and returns true on Clang. But this is only up through Clang 10.0. All the Clang versions before 10.0, this static assert fails. But all the versions of Clang after 10.0, this static assert succeeds. By the way, the other failures that I talked about, those fail on every version of GCC and Clang that I tried. I don't know about the Microsoft compiler because I've never used it and I didn't really try it. But so, practical application of void T. It's awesome. You should use it. It's like sliced bread. It's awesome until it's not. But it's not void T's problem. It's this core language issue that we just have to hope will get resolved one day, and then std void T will magically work like we expect it to work in all contexts. Until then, I use my own void T, just because I don't like having to have situations where things work in some cases and don't work in others, because I don't like having to remember when they work and when they don't. Also, when you're doing template metaprogramming or metaprogramming in any case, or when you're doing programming in anything, right? But especially when you're exercising the compile time stuff, because there are vastly more people that are doing normal programming things to exercise the compiler than there are doing metaprogramming things. And so there's probably some issue that you're going to encounter. So always build and run tests in both debug and release with at least 2 different compilers. Let me go back here. So are there any questions up to this point?
My question was about your next slide.
Okay, all right, then save it. All right, great.
Have you noticed any binary size changes when using your custom void T compared to ST void T?
Okay, the question is, have I noticed any binary code sizes from using my void T versus the std void T? And no. In fact, what happens is all of these things are gone away at compile time, right? The compiler will use a little tiny more memory because my symbols are longer, and probably because there's a bunch of other stuff that's already instantiated void T for some of the things that I've instantiated it for. And so it's already memoized it. But other than that, there's been no effect. And I've used it a lot, and I've not seen any. And in fact, before there was another core working group issue that didn't like you having template parameters that you didn't use. That actually, and so before that, you actually had to use void t as an indirect, what I call an indirect alias template. Once that one got fixed, now you can use it, but it still doesn't quite work in some contexts. In C++20, do I have any preference for when I use void t versus requires? And the short answer is not really, because I've not had too much opportunity to use C++20 a whole lot in anger, except just in testing it in situations, right? I wonder if this works. No, that doesn't work. I'll try the compiler next month. Does this work? No, that one doesn't work, but this other one does now. And but I think that as concepts come along and as we have requires, I think that we should prefer those methods over any of the previous ones. They're easier to use and they're more clear. However, remember that the concepts still have to be implemented, and concepts are just they're a Boolean, a compile time Boolean expression, right? So a lot of times what you're trying to do is this a valid construct? And still, I think we still need something like void t or something else to tell us if some of these constructs are actually valid at certain times. I know that when we use a requires clause, you can put them in there, but when you're trying to build up some of these things, especially if you're trying to use code that maybe there is, but I haven't met anybody yet, I've been asking, that uses just C++20. Everybody I've asked that's using 20, they're using 20, but they're also at least supporting 17 and things that don't have requires. So, yeah. Yes, enable if works there. Enable if does work there. Yep, you can use enable if there. It's possible. Remember, enable if, you have to have a Boolean value that is there, right? And you can construct Boolean values from some of these, but when you're just trying to check something about the types, void t, in my opinion, is much more clear, easier to use. If I'm checking a Boolean expression, yes, I will use enable if. Actually, I use a different form of it that I call choose, and what happens is it takes a Boolean expression like enable if, but it also takes a ... And so it resolves to an alias of enable if, the expression, and then the void t of what I want in the end with those ... So you can do both of them at the same time if you want to. Yep. Yep. Anything else? All right. So anytime you start talking about doing compile time things, or anytime you start using them, right? If you've been using them for a long time, then you know most of this stuff. If you're new to them, you're probably afraid that if I use a lot of this metaprogramming stuff, my compile times are going to slow down. And you're absolutely correct, because anything you use, you're going to pay for. But how much do you have to pay for it? For me, I treat compilation performance just like I do runtime performance. In that, don't prematurely optimize. Don't prematurely pessimize. I'm not sure that's actually a word because the spell checker wouldn't let me spell it. I had to force it to spell it. But I use it, so that makes it a word to me. And code is written to be read by humans. Compilers can read anything. This is especially true when we start working with template stuff, or we start working with metaprogramming, even const expert things. Because of the restrictions at compile time, sometimes things become even more hard to read. And even in some examples later in the talk, you'll go, wait a minute, I thought you said you wanted things to be easy to read. And that's true. It's still difficult sometimes. But the most important thing is actually measure. Well, you say, how do you measure compile times? Well, up until a couple of years ago, the only real way to measure was to have your own framework and measure complete compile times. It was really hard to actually find out what does it take to compile this particular template or this particular thingamabob. And so we need something to measure with. Clang has some great measurement tools. In particular, with Clang 9, there was this command line option that was introduced in Clang 9 called -f time trace. It is my all-time favorite compiler option. Unfortunately, I haven't seen GCC. Anybody know if GCC implements this thing or not? No? All right. How many of you guys are aware of this -f time trace? Okay, so a number of, okay, about half of you. Okay, good. This is my favorite compiler option. Because what it does is it generates a JSON file alongside your object file, and that JSON file is like, have you ever instrumented code and tried to do performance analysis of runtime code and you get an instrumentation? It's the exact same format. And you can use the exact same tools to analyze all of your compilations. They can be loaded into both Chrome tracing and SpeedScope. And we'll see in a minute what it looks like. But first, we want to measure something. We want to have something to measure. Back in December of 2019, I had some time on my hands over Christmas, and that's when I found out about this thing. And I caution you, if this is your first time finding out about it, stop looking it up, and don't try it until you have a full day of nothing to do. It is compiler crack. Because once you start playing with it, you're not going to want to stop. I took vacation so that I could just play with this thing for days. This, looking for a type in a list of types is a very simple, easy thing to do. But it got me interested. What is the performance on this? I literally implemented it probably in, I told Robert the other day, 40 ways. I went back and looked, it's probably closer to 80 different ways of implementing the same stupid thing with just minor tweaks on things to see what the performance is. Because you can actually see that granularity. So what we're going to do is we're going to implement this thing here. I'm going to go over it in a little bit of detail because this might be new to some people because this is a tutorial, right? So this is basically, the concept here is we're going to find a type, a target, that's our type, and we've got a pack of types, a list of a bunch of types, and we're going to look for it. And the first thing we're going to do is we're going to try this recursive. Now, there is one thing you'll note is that, and I left them in here for this purpose, you'll see this recursive underbar is in pack. And that's because I have a couple of nitpicks with the implementation of the tracing. And one is that it strips out namespaces sometimes, and so it doesn't, and so you don't have, I can't key on the namespace when I'm looking through it in the JSON, right? So I wrote a program to take the JSON and pull out all the times that I was interested in so that I could time everything. So I gave them these big long names so they would make sense to me. But if we look at here, the first thing is the primary template. The target type wasn't found. It's a false type. The next one is the target type is the first type in the list that we're looking for, right? Notice target. We come down in the instantiation, the specialization. The first parameter there is target T. It matches, the first argument is target T, it matches target T. All the rest of those match with rest T, right? That's what they're going to match. That's the rest of the list. And so we see that the first item in our list of types is the one we're looking for. And so we found it. And so we return true. Yeah, I found this thing. And then this is when we haven't found it, right? Because the first item in the list of things we're looking through doesn't match our target, right? So it's just recursive. We have a list of things. We know our target. We look at the very first one. Is that the one we're looking for? Yes. Oh, I'm done. I return true. We look at the one. No, that's not the one I'm looking for. So I will continue on with the rest of the list. And so that's what this is doing. It's inheriting from recursive is in pack, target, rest T's. It's saying, okay, now I'm gonna recurse. I'm gonna go back to the top. I'm gonna inherit from another class and let it look in the rest of them. Because all I know how to do is compare, am I the first one? Is the first one the one I'm looking for? That's all I know how to do. If it is, I'm done. If not, then I need to ask myself again, or ask a version of myself again, hey, can you check on the rest of them? So this is a scoped output of running this JSON file through the scope trace. That is awesome. That is just awesome to me. It's basically a flame graph of all of your compilations. You actually can get your whole entire compilation and see how long is each header file taking to compile. But not just how long each header file, how long each instantiation. You can look on here. This is recursive. You can see all the little recursions, each one of them, and how much time each one of them took. And as you go to the top, that's the cumulative time. Okay? So if you want to figure out what your compiler is doing, use Clang with this option, and you don't even have to write any code for this. You can just take your JSON file and shove it into either of those two tools. And they'll show you the graph, and you can look through it, you can drill down as far as you want, and you can see where you're spending time. So if your compiles are slow, figure out where you're spending time and change what you're going to do. Well, how is really changing implementations of something at compile time going to buy you that much of a difference in speed? Well, let's look at the compilation times. And I basically got these by just writing a stupid little program that parsed that JSON output file and looked for the things that I was looking for. And what I did is I wrote a test harness that took some number of, and it made some number of unique types. Those types were basically, if I wanted 32 of them, it would basically expand and do an integral constant of 0 up through 31. And it would create a list of all those, and then the driver would go and look for each one of them. And then it would turn the list backwards and look for each one of them in the backwards list, because some of the things were much faster going one way than going the other. And then I had a baseline that was doing all of that stuff, but then its lookup was just returning true, right? And so I took the times and subtracted them from the baseline. That's the times that we see here. So in the top is the number of elements that were in the list. Along in the columns underneath them, that's the amount of time that it took. And if I remember correctly, and actually I did rerun these times this week, okay? And what I did is my script ran through them, and it ran the whole program, and it ran it each time through each one of these sizes 10 times, took the mean, the max, took the min, the max, and the mean, so that I could make sure, because I mean, it was on my on my Mac, right? So the times, you'll probably get better or worse times depending on what you do, but they were very, very consistent. So to do recursive, I'm pretty sure these are microseconds. I can't remember, but I'm pretty sure that my conversion was to microseconds. So that's how long it took to do the recursion lookup. Okay? So let's do a linear search. Jody, did you even go to computer science classes? You just did a linear search, right? That's what I did. I implemented a recursive linear search at compile time. Well, I'm going to implement another linear search at compile time. But I'm going to cheat a little bit. Remember, this is practical application. This here is not standard, okay? And I know it's not standard because, well, it's not in the standard. But also, it doesn't work on Windows. There's a thing called under sig, under that I think that's what you use on Windows, and it's very, very close. Now, I will tell you, there are a couple of caveats if you're using this. If you have a class that uses non-type template parameters with auto, and you have template auto something, struct foo, and you instantiate foo with 42, that's an int, 42. And if you instantiate foo with 42u, that's an unsigned int, 42. Those are two completely different types. Two completely different types. The compiler will even tell you they're two completely different types. But you will get the same string. So if you do something like this, like with the hash map or things like that, then you'll need to at least put a check in there to make sure that all the stuff that you're comparing against, that they're all comparable with one another. In that what you get by looking it up is different if and only if the two values are different, right? Clang 11 fixes it. So in Clang 11, you will actually get the right thing, okay? But nothing before Clang 11 and no other compiler that I see. So in here, I've just declared a function on a type. I'm not using this right now, but I use it later. You could have it be a null function, but I think somebody told me that Microsoft will fold even your template unique functions that they have the same implementation, will fold them into the same one, and so you're not guaranteed to get the same pointer back. Somebody told me that. I didn't believe it, but somebody told me. So here's our implementation. It's very, very simple. You basically go through and create a constexpr vector or constexpr array of these these function pointers, right? That's what this is. It's an array of function pointers. And I go and create them using ... which, by the way, is not a fold expression. Just because you use ... doesn't mean it's a fold expression. You can do that in C++ 11, right? The ... part at the end. So that's basically saying, go and get me the address of the name of function for each type that I've given it into this list. So for each one of those T's, IDs is going to be an array of function pointers. Those function pointers are guaranteed to be unique. So then what we're going to do is we're just going to ask. We're just going to ask, is it in there? And whenever we're asked to look up a function, it's going to resolve to the function pointer, ask us if it contains it, and just do a linear search. And all that should be pretty basic. There's no template-y special stuff. It's just all constexpr stuff. You can use std find on C++ 20, but you can't use it before that. And this is the performance difference. Remember, they're both linear searches. And one of them is actually creating an array of all of them and then going through and doing the search, okay? So it depends. So if you're doing small things, it probably doesn't matter what you use. And in fact, if you're new to this stuff, I encourage you that you should, if you're allowed to use Boost, you should probably be using Boost HANA. Because it is by far, in my experience, it is by far the easiest, most full-featured thing, best way to try and do stuff at compile time that doesn't twist your brain and force you to enter into the type space, right? I've lived in the type space so long that it almost seems a little unnatural for me to do type thinking in that way, but it is awesome. So you probably should be using that. It does, however, merge into these different spaces. And so if you're doing stuff that's doing a lot of compile time things, like complex state machines or doing lots and lots of type maps together, then you do pay for performance for the convenience and generality of it. But in this case, we see that there's a vast performance difference between these two. Well, what else can we do? Remember I told you I implemented this like 80 different ways. We're not going to go through all 80 different ways. So this one is basically just using inheritance. And that right there just says, go grab the type identity of each one of these and inherit from each one. Right? I've got this implementation. I'm going to say, all the types you give me, I can't inherit from each one of those types. Some of them may be ints, or maybe even be a void. But I can inherit from a type identity of that type, and each one of those is guaranteed to be unique. So I can inherit from each one of those. And then down here, when I do my check, I can just check to see, and I take the implementation, and I grab a pointer to it. And I call check. And if it can be converted to type identity of T, which means that it inherits from it, then that function is the one that would have gotten called. And so that will be true. However, if it can't be converted to that, then it means we don't inherit from type identity of this, and so it will be false. Note, however, there's a limitation to this that the previous two implementations did not have.
You have two types if you have duplicate type in that, it will fail.
Exactly. It does not support duplicate types. If you have multiple types in here, you're going to get a hard error, and there is no way I know of to sphene that sucker away. That's a hard error that you're going to get, right? But if you have multiple types in there, it doesn't work. So there's a restriction on this. But if you're willing to say, you know what, I'm okay with having only one type in there, then you do get a performance win. I stopped recursive at 512 because I just didn't run it after that. It just didn't seem, it was wasting my time. But you can see that this inheritance is much faster than the others. And so there is a win. You do have to pay for it with, I want it to be unique. Now, you can get around that easily enough when you inherit. If instead of inheriting from type identity, you inherit from struct, size t, comma, type name. And if you inherit from that and then have it inherit from type identity, then you can do two things. You can virtually inherit from each one of those, and then it works fine, no matter how many they are, but you pay for the virtual inheritance too. You don't have to even do the virtual inheritance. You can linearly inherit from multiple of these. They all inherit from this stuff. You can't, however, do the trick that we did there by making it cast to it. But our wonderful compiler has a type trait, is base of. And even if you have multiple bases of the same thing, you can call is base of on it and it will return true or false. It does not have the same limitation. And the performance difference, I didn't put it in the slide, but the performance difference is about 20%. Not that bad. So, but compilation times can differ. Now I want you to note, this implementation is the exact same as the previous one, except instead of the check taking a pointer, which is what it did before, it just takes it by value. And down when we pass it by value instead of by pointer. But it's happening at compile time. And you know what? It's really not even instantiating it because, what's going on? This is happening at compile time. There's the numbers. So the difference between, if you implement that by having it cast to a pointer or to a value at compile time, if you're only doing 32 or so, who cares? Pick whichever you want. But doing that kind of stuff really does have an impact on your performance, at least on Clang. And when you're implementing big, huge things at compile time, those values start adding up. That's a tremendous amount of time. So this one is just slightly different than the other one. If you remember the other implementation, we'll go back so you can see it. The check functions they're free. They're in a namespace. They're not inside of the struct. But this implementation, they're static inside of the struct. That is the only difference between these two implementations. Everything else is the same. They both take values. What are you paying for that? I like putting stuff inside structs. I like composing them in there so that they're kind of hidden away. But man, you pay for it. You pay a lot for it, really. These implementations have only just done by small, but they have significant impacts on performance differential. So practical application, yes. I'm sorry? Yes, I did is same T with a fold, and it's horrible. It's horrible. You asked me Did you try this? Yes. I mean, I literally have a whole thing of all these things. And is base of. Using is base of is almost as fast as the fast inheritance with the pointer. Until you get up to 512. After that, it falls off pretty good. But up to there, it's actually really good. And the thing is, it's really, really easy. Because you just say, is base of ... And it just goes, yeah, man. You know? So if you're doing small stuff, likely not an issue. If it becomes an issue, then measure. And now you have a tool with Clang to measure. There's no guarantee that you're going to have the same performance characteristics on GCC, though. So what then you have to do is do big, bulky comparisons between Clang and GCC. GCC, if there's somebody doing GCC work, maybe put this in. It would be kind of awesome. I'd like buy you a donut. I'd even buy you a beer if that's what you want. Currently, I know, it's only supporting Clang, and you can process the JSON is documented. I mean, the format's it's normal format document. Be careful. Seemingly similar implementations can have extremely different compile time characteristics. Anybody else have any other questions about that? Performance is always a big thing, and just like runtime performance, measure. If you've not used this tool, start using it. It's a great, great tool. However, it can generate big JSON files. So when I did my 1024 with all of my implementations, I had a 4 gigabyte JSON file that I then had to parse through. Yes?
With your pre-functions implementation, did you observe a difference between fully qualifying the name from colon versus using unqualified name lookup?
That may be one of them that I didn't try. I can't remember. I can't remember. But that's something I'll go back and look. Yes.
Can you repeat the question?
I'm sorry. The question was, did I notice a performance difference between doing unqualified lookup versus qualified lookup of the functions that were in the namespace? And I don't recall if I did that or not, so I don't know what that would have. Yes?
It looks like MSVC also supports this thing. So they've got something called VC-perf that can also generate these things.
Oh, awesome. So the comment was that John says that he thinks that MSVC also has something like this. And what's the option called?
You run a program called VC-perf, which watches all the...
Okay, you run a program called VC-perf, which watches all the instances and then gathers similar information. Okay, great. So, sorting types. There's one question, why? Well, actually, I have a really, really good example, but that was when I thought I was going to do like I have 2 hours to do something. And that example is really hard. However, Chris Jusiak, the other day, he basically showed his names tuple thing. And he said, oh yeah, and what would be good is if you also probably want to pack these types based on their alignment. And he left it as an exercise to the reader. And so I'm like, all right, I'm a reader. Look, the best C++ programming book I ever read, that's just me, but I love this book, but it was written in 1992. See, old things still have value, says the dude in the white beard. This book is invaluable. If you haven't read this book, don't not pick it up because it was written in 2002, 2001. It is awesome. Template metaprogramming, that is the bomb.com. Man, my kids are going to kill me if they hear that. It is awesome. Even today, it doesn't have any C++ 11 stuff in it. But the principles, the characteristics of what's in there is flat out awesome. Read them. Okay, so we're going to sort some types.
For the YouTube, could you say what those books are?
Oh, sorry, yes. I was holding these books. Advanced C++, Programming Styles and Idioms by James Coplian. C++ Template Metaprogramming, David Abrahams and Alexei Gertvoy. I always get the name wrong. And Modern C++ Design by Andrei Alexandrescu. Those were the books. Okay. So if we look at this, this is just it's the top part of the class. Not really that interesting, but it tells you what's there, right? It takes a template called orderable that allows you to provide some order for the types that you're comparing, because types don't have implicit ordering. And you basically give it some list. Then it gets specialized with orderable, with the list template that you're giving it, and the types, right? And then you see in here the implementation, there's an impl that takes a seek t, takes one type. There's an impl that takes one type. Well, here's what that impl is. That impl takes a bunch of size t's. This is a technique that if you're not familiar with, this is a powerful technique no matter what you're using, right? This is a very powerful technique of being able to have these index sequences. And so this is a type, which is an index sequence of a bunch of numbers that start at 0 and go up through size -1. What we've done here is we've created a static constexpr array of indexes. So we're creating a static constexpr array. We call it indexes. What is it? We've got a little squiggle thing over there, so something important is in there. And we see the 2 brackets there, so we know this is a lambda. So inside, in order to make things kind of a little bit easier to read, we take the types of all of our orderable values, and we get the common type of them. Okay, that's all that's doing. It's taking all the types that we've given it, asking the orderable for it to give us the type, give us the value, and we're taking the type of it, the common type of it. We're creating a pair, and the reason is because only until C++20 could you actually do some things at compile time with std pair. So this is just all we're doing is we're taking each type is going to define an orderable attribute, right? Whatever that orderable attribute is, it's some object that has to be orderable. It has to support less than, right? And I think I have it support equal to, but maybe just less than, depending on what your sort is. And so then we're going to create an array of pairs. And the pairs are the orderable for that type and the index that type lives in the parameters that you send it, right? You sent it a bunch of types. And the index sequence basically has the same number of things in it. Each one of them is the index of the type, right? So if you send it 5 types, type A, B, C, D, and E, then the index sequence is going to have 0, 1, 2, 3, and 4. And so type A is coordinated with 0, type B with 1, C with 3, and that's as far as I'm going to go on the alphabet because I already did that earlier. So this is basically creating an array of pairs where you've got a value that is going to be sortable. It's going to be orderable. And the index that type lives in. And then we're going to call std sort if we're in C++20, but we're not. This example is not in C++20. So we're going to call this stupid insertion sort that I wrote that you don't need to see because it's just like any insertion sort that you ever wrote. And what this sort is going to do, it's basically going to takes the array of orderables and indexes, and it sorts them based on the orderable field. So after this sort has called, that array of pairs, where each one was an orderable and a type, an index, is going to then be sorted, right? So that's what we're going to have. And then what we're going to do is we're going to return an array. And the array is going to be of size. Basically, it's going to be the indexes of each one of those. And it's going to be the same size as the t's. And we're going to go look in this array, and we're going to say, okay, sorted array by the orderable, give me the index. So if the third type was the smallest quantity, it will now be in the first spot. But its index will be 3, or 0, 1, 2. Its index will be 2, right? And then we're going to immediately invoke that lambda because we're assigning its result. We're basically sorting the types, putting them into a vector, into an array, and then we're going to return it as the constexpr. Okay? And then we're going to say the type is the list, which is the template, the argument that you passed in. You can do this with std tuple. You can do this with type list. You can do this with whatever your favorite listy thing is. And we grab the element and the types. And so then what we're doing is we're taking that index and we're saying, okay, grab me the one at that location. And here's where we invoke, where we pass it the index sequence. We make the index sequence that we pass to it. And now we can do this. We can say orderable is integral constant align of, T. And we can say sorted equals sort types, pass it the orderable, pass it this type list or a tuple of things, and then we can assert that the type list is now char, int, unsigned, and double. Now, if you were using this really to align and do your packing, you can't assume what your std tuple is going to do, especially if it inherits it because the standard says nothing about the order that they're going to be in. You're probably good if you sort it. It's probably going to be the best you can do, unless you then run next permutation and go through all permutations and check them out. If you want to sort types here, I've got to run here quickly. So this is how you could do it generally. This is a type ID that gives a unique number, a unique value for a type using that string, right? That string view. So they're comparable. And so I give my type comparable or type orderable, which is just the value of the type ID. And then I can, so one of the things that bothers me like with std tuple of int, char, and string is different than std tuple of string, char, and int. Sometimes that's what you want, but sometimes it's not. I mean, if you have a struct and you've got int x, char y, string z, does it matter which order they're in as far as how you want to use them? So you can normalize your tuples by just sorting them with that and saying normalize tuple, and then you've got your assertion that take each one of those tuples, normalize them, and they're going to be the same. Okay? And I think I'm out of time. I think we might have time for questions until, yes, we do. So if anybody else has any other questions, throw them at me. Hana, H-A-N-A. Yeah, and if you're into just doing something extremely unorthodox but really, really fast, there's another Odin's library called Kvasir, K-V-A-S-I-R, I think, that was designed to be optimal in a bunch of cases. But Hana is the place I would point people to if you want a library to use. Yes. The question is the reason for sorting these tuples, right? That's basically, and the reason is that if I call normalize on a tuple of int, char, and string, and I call normalize on a tuple of string, char, and int, I don't know exactly what I'm going to get, but it will be the exact same for each one of them, right? So I can then just say, hey, I just want the normalized thing so I can pass them around. Oh, I'm taking a tuple of int, char, and string, but somebody passed it a tuple of string, int, and char. You know, those two things aren't the same type, so they're not going to compile right. But if you use it as the normalized type, then that's a way of kind of normalizing that thing away so that your type is adjustable, right?
Is empty supposed to be always initialized, or is it supposed to be like the pre-function?
No, empty is default initialized because that is the value that you get if you have a default constructed type ID. It's nothing, and nothing will ever match empty except a default constructed type ID. It's the default value.
So for your operator less than, is it like multiple default constructed string views not less than each other?
Well, what we can do, we're gonna get booted, but I can stick around and answer. I can explain this in detail if you want. Did you have something in the back? Okay, yeah. I'll move around then. So the empty, I know this doesn't help for the people that can't see, but the empty is a static value. It's a static string view, right? and it's going to have a unique address. And that address is what you're using for the SV. So if you default initialize a type ID, its value is going to be the empty one.
Right, but you're dereferencing that pointer in your upper to left.
Yep. Oh, yes. Yes.
Aren't you just comparing the default constructed string?
If the two things are default constructed, yes. But this member function right here, type ID, this friend member function is the one, it constructs this thing. Oh, I guess I didn't show that type ID. It constructs this SV by calling that thing, that name type that I showed earlier. It calls that to get the string view value, which is guaranteed to also be, and then it grabs it in here because it's going to keep it. Does that make sense? Yeah, that was hidden. This thing is how you create them. And I think I showed that
So it's unique.
in there. I'm sorry?
So it's unique.
It's unique by pretty function. Exactly. It's unique by pretty function. It's unique by the string that was returned by pretty function. And so if you use this with those ones that have the auto non-type template parameter, it may or may not work. In the actual code that I use for this, I actually have a check for any of them. It runs through them all when you add them in to make sure that they're compatible, and if not, it gives you a nice compiler error. But I mean, it's a slide and it's talk, but and you know, I copy pasted these, so and then as you're trying to change them, I might have, but I would be happy to go through more of this with you guys if you want. Am I out of time? Do I still have time? Anything else? All right, I'll be around till tomorrow. So if you want to talk to me about this stuff, let me know.